afternoon, first of all, and as he said, my name is Teresa Garay, and I'm an intern with the UC Leads program here, and I'm here on behalf of the Read Research Group and my mentor, Gesine Vates, both in the Organic Chemistry Department here at UCSB, and I'm here to speak to you about the synthesis of 4-amino-cyclopentenones via aza-Piancatelli rearrangement using a polymer-bound metal catalyst. As he said, very complicated. So first of all, I'd like to introduce the idea of natural products and their significance. So compounds such as Taxol, as shown here, which many of you may have heard of, can be and have been isolated from nature, hence the name natural products. More importantly, though, is the fact that many natural products actually have biological activity. And so it's great that we can see these compounds out in nature, but it's crucial, especially for the treatment of diseases. For example, Taxol is used as an anti-cancer alkaloid. So it's crucial for the treatment of diseases to be able to access these types of biologically active molecules in the laboratory setting. So this is where synthetic chemistry comes in. And so in talking about natural products, there's certain different classes of natural products, and one of the main subfamilies that the research group that I'm working with focuses on is that of one containing a cyclopentane 5-membered ring. And so more specifically, a cyclopentane scaffold with a nitrogen attached. And this type of structural motif is widely represented in natural products such as cephalotaxin, as you see here in red, a 5-membered ring with a nitrogen attached here in blue. And even in some drug-like compounds such as this NK1 inhibitor, which has a 5-membered ring here in red and again the nitrogen in blue. And so it's important for us to be able to make these types of structural motifs in the laboratory setting, and therefore take a step in the synthesis of the more biologically valuable molecules, the total molecule. And it's not only important to be able to synthesize these, another step in this would also be to be able to synthesize them in a more green manner. So when I say green, more efficient and with producing less waste. And this is where the idea of continuous flow chemistry comes in. And continuous flow chemistry would be a technique that can be used, like I said, it's more efficient and produces less waste, and that not only has importance in the chemical industry, but also in the process of regular benchtop laboratory chemists, synthetic chemists. And so thinking of the idea of the research group that I'm working with, that they have looked at the Piancatelli rearrangement, which uses a fluorocarbonyl with water and a protic acid to afford a 4-hydroxy cyclopentenone. And so what the lab, some of the people in the lab that I'm working with have developed an aza-Piancatelli, aza for nitrogen. So they've used a fluorocarbonyl replacing water with a nitrogen species, as you see here, and instead of a protic acid, use a powder Lewis acid catalyst, in this case dysprosium triflate. And it affords a 4-amino-cyclopentenone. So a 5-membered ring with a nitrogen, which is similar to the scaffold that I was talking about earlier up here with like this. So this allows us for a first step in certain syntheses like drug-like compounds like this. And so what my project entails is applying this sort of reaction in a greener sense. So in my project, I undertook the investigation of a polymer-bound catalyst in that reaction. So I replaced the powder Lewis acid catalyst with a polymer-bound Lewis acid catalyst. And I was hoping in this to develop a comparative analysis between the two forms of the different catalysts and to see the differences between the yields and reaction time and efficiency and degradation and all these different properties of the two different catalysts. And so for these reactions that I was running, I used two different furocarbanols, paramethoxyphenylfurocarbinol and the phenylfurocarbinol seen here. And I reacted those furocarbanols with para-iodoaniline using the Palmer-bound metal catalyst. In this case, Palmer-bound scandium triflate, which is commercially available. And this hadn't actually been tested, this Palmer-bound catalyst hadn't actually been tested under these circumstances. So this is quite a novel idea, so we were still trying to see if it would actually work. And so in running these reactions, there's a typical laboratory process that we go through. And so first of all, most importantly, is to set up a reaction. We need to put in all our reagents and solvents and make something happen. So first of all, we set up a reaction, and we then monitor it. We need to check the progress of the reaction, and sometimes it may take 10 minutes, sometimes it may take a couple hours, sometimes it may take a few days. So taking TLCs, thin layer chromatography, it allows us to check the progress of our reactions. And so once you see that your reaction has gone to completion, you can go ahead and move on to a next step. And so next we want to just isolate what we actually made and get rid of excess liquids and solvents that we may have had in our reaction. So for this, we use a rotary evaporator. It just increases our efficiency of evaporation of solvents. And finally, when you have your product isolated, then you want to purify it. And because not all our reactions are very clean, so you want to purify it from any impurities produced in the actual reactions. And for this, we use flash column chromatography. And in this case, I used a silica gel column, which separates based on polarity. And then after you have that, after you purify your product, you want to know if you actually made what you wanted to or what you expected. So for that, we use NMR, or nuclear magnetic resonance. And it's sort of like taking a picture of your sample. And a machine like this, NMR machine, produces a peak spectrum like this. So depending on where your signals show up in which regions, you can assign a certain functionality to your molecule and therefore confirm its structure. And so when you finally confirm its structure, you want to weigh out how much you actually made. So that was one of the main things that I looked at, was seeing the actual yields that I got using the Palmer-bound catalyst. And so summing up about a month or a month and a half's worth of work, I ran the paramethoxy phenylfurocarbinol, and I saw that the results across the board, I ran 5 different trials and reused some catalyst beads as well. I saw that the results were quite consistent across the board. And so the average for the 5 trials that I ran was an 86% here, and compared to the powdered scandium triflate, which was 89%, you can see that there's only a few percent difference. And so this kind of suggests to me that both forms of the catalyst have similar activity. With the phenylfurocarbinol, I also saw consistent results, but notably here, I ran these reactions at 80 degrees compared to the other one, which was only at room temperature. And so what these results suggest to me a little bit further is that the beads withstood some heating cycles. And so again, you see here that 88% and 92% between the average of the polymer-bound and the powder catalyst is quite comparable. And so what I concluded throughout seeing all these results was that the yields are comparable, and the activity of both forms of the catalyst is similar. And so also the catalyst can be recycled, as far as I know, from these 5 trials that I've run in both different reactions, because they didn't show degradation or instability even after using them 5 times. And so also the yields were quite consistent across the 5 trials that I ran. And so this also shows to me that maybe the beads are tolerant to air exposure and even heating cycles of 80 degrees Celsius. And what this creates is a potential for using a greater mole percentage or a greater concentration of our catalyst in our reaction, and therefore possibly speeding up the rate of the reaction without actually having any negative effects of using too much catalyst. No worry about the waste, since it can be recycled. And so there's still much work to be done. In these short weeks, there wasn't a lot that I could actually do, but in the future, I'm hoping to test different fluorocarbonyls and different amine species as well, using the polymer bound catalyst, and also investigate the especially low yielding reactions that my mentor and others have run, and see if maybe the polymer catalyst behaves a little bit better in producing better yields in those. And I think ultimately the ultimate goal for this project is to help build a continuous flow reactor using a solid supported polymer bound metal catalyst, in which you can just pump in certain reactants into a column that has your immobilized catalyst inside, and out comes essentially only your product with no real waste involved. And then if this is an intermediate in a different synthesis, then you can just put this connected to a different column in which you can just keep proceeding with the steps in a synthesis of a molecule such as this. And so with that, I'd like to thank you guys, and I'd like to thank Dr. Javier Ruiz-Alanis and my mentor, Gesine Bates, for their great patience and allowing me to contribute to their projects this summer, and also the rest of the Ruiz-Alanis group that is here as well, for sharing their lab space, their very tight lab space, and for imparting some knowledge for me and helping me become a better organic chemist. And also Erica and Matt and Ophi and all the rest of the UC Leads people who helped really make this a meaningful experience and a great success. So with that, I'll take any questions.